friends. Today I'm going to do some advanced elasticity problems on what I call analytical functions, functions without numbers. But first I'm going to introduce something special I'm working on for you guys called the mother of all elasticity handouts. So here's what it looks like so far, and this is definitely a rough draft version here. Kind of taking off of the mother of all consumer theory handouts that I made a couple of years back. I started thinking about what are all the things that I'd want to say in kind of an advanced review refresher of elasticity, and also talking about some more of the advanced things that you need to know if you're in a master's or PhD program about elasticity. So just a very quick tour so far, and I would love to hear your thoughts about what I need to add here. Introductory points about how elasticity is a measure of responsiveness. Elasticity is unit free. The basic idea is you want a percent change in one thing divided by the percent change in another. And the first word in elasticity is the percent change that goes in the bottom. How to interpret elasticities if you're talking about numerical things. Some of the details we need to remember about price elasticity of demand, the total revenue test, common elasticities in addition to the price elasticity of demand, some advanced stuff here about elasticity of a point, where the elasticity at a point formula comes from, brief derivation, and looking at the basic idea using calculus. And here I go through an example using a numeric example with a Cobb-Douglas demand function, not to be confused with a demand function that comes from a Cobb-Douglas utility function. A little bit on econometrics here and why you can use a log-log model to estimate elasticities, and a little bit about what the assumptions are there, and then a little bit on what we're going to do today, elasticity with analytical functions, starting with a Cobb-Douglas. So if you have a demand function for a Cobb-Douglas, how do you use this formula? The elasticity of demand is the partial derivative with respect to price times price over quantity to come up with elasticities for the price elasticity of demand. And we'll also look at the income elasticity of demand and the cross price elasticity of demand. So for today's video, let's jump into doing that. So as always, I encourage you to download this handout that I'm using today, and I will make a PDF of it and include a link in the description to this video, as I try to normally do. So let's jump into the meat of today's problems. You guys love to watch me do math problems, and I don't like doing them, but I understand the need for doing this kind of thing. I know the disconnect that there often is between seeing a formula like this, and you kind of know what it's doing, you kind of know what it's telling you to do, but when the rubber hits the road and you actually need to use it for an applied problem, you're hesitant, because this isn't the kind of thing that you do every day, and it's not the kind of thing that you're taught to do in math classes quite often. So I understand your feeling. So let's dive in. So if we have a Cobb-Douglas utility function here written in the standard form, constrained, and we're calling income M here. We're calling the price of good X P. We're calling the price of good Y Q. When you're done with all that, here are the Marshallian demand functions. X star equals alpha M over P, Y star 1 minus alpha M over Q. So suppose we wanted to take those functions, and we're just going to focus on the one for X here. Suppose you wanted to know the own price elasticity of demand, the income elasticity of demand, and the cross price elasticity of demand. Let's derive these things and see how to simplify them here. So, as this function says, what we want to do is just take the partial derivative of this x function with respect to the price of x, and then multiply it simply by p divided by x. So, taking the partial derivative of that function with respect to p, we can a little bit more easily see what we're doing here if we rewrite this as alpha m times p to the minus 1, right? That makes it crystal clear what we're doing when we're taking the derivative there. Multiply by the exponent. So we're going to have minus 1 times alpha times the budget times p, and then subtract 1 from the exponent, p to the minus 2 power. That's the partial derivative part, but then we have to multiply times p over x. When you have this p over x, you don't usually want to leave this x sitting there like that. What you want to do is replace it with this demand function version of x that we have here. So we want to divide by alpha m over p. Let's go ahead and replace that with alpha m over p. And then what we want to do is start simplifying. Now, one thing we could do to simplify here, right off the bat, that's just going to make it a little bit easier to see what we're doing. Instead of dividing by a fraction, let's multiply by the inverse, right? When you divide by a fraction, you can also multiply by the inverse of that fraction, and that's just going to make it a little bit easier to see what we're doing here. So let's take p divided by alpha m, right, and just kind of multiply p by that. And that's going to be a little bit easier way to see how we're going to be simplifying here. Because look what's happening. We have p squared here in the numerator, and we have p to the minus 2 here in the denominator, and those are going to cancel. We have alpha m in the denominator, we have an alpha m here in the numerator, and those are going to cancel. And so what we're left with is this startling result here, that the price elasticity of demand for a Cobb-Douglas utility function, right, for the Marshallian demand that results from that, the price elasticity of demand is always simply -1. All this other stuff just goes away. So that price elasticity of demand is just -1. Everything else cancels. It's great when everything cancels and simplifies our life, isn't it? All right, well, let's do the same kind of process, but let's look at the income elasticity of demand. So the income elasticity of demand, instead of looking at the price, everywhere here we see price, we just replace it with the income. So as long as you start to see these patterns, this doesn't become quite as hard anymore. So let's take the derivative of this with respect to m now, and let's just bring this over here so that we have it nearby. So we want to take the derivative of that with m. That's going to be pretty simple because the m is just to the first power. So we're going to be left with alpha times p to the -1, and then we're going to multiply that times the budget over x. But as before, we don't want to just leave that as an x. Convert that into alpha m over p, or alpha m to the p -1, however we want to write that. I guess leaving it this way in this case is probably going to be the easiest way to look at it. Just plugging in this way of writing x down on the bottom, because here we can clearly see some things that are going to cancel. The m and the m are going to cancel. The p to the -1 and the p to the -1 are going to cancel. And the alpha are going to cancel. Wait, everything just canceled. So what does that mean? Well, that means that what we're left with is, again, kind of an interesting result that you might not expect if you haven't seen this before, that the income elasticity of demand for this Cobb-Douglas demand function here is always 1, constant at 1. All right, well, now let's look at the cross-price elasticity of demand. All we're doing is replacing, instead of looking at the relationship between the amount of x purchased with respect to price or with respect to income, now we're looking at that same relationship, but with respect to the price of the good Q. So again, we have our little friend here. That's our demand function, and we want to take the derivative of that with respect to Q. I don't see any Q's there. So the derivative is equal to 0. And then we take that and we multiply it times the ratio of Q over M. Well, it doesn't really matter what we're multiplying it by, guys. It's just 0. And this should kind of make sense, right? If we look at this demand function here, Q is not involved. And if you're familiar with the Cobb-Douglas Marshallian demand function and working with it, either numerically or analytically, you see that since there's not a Q involved, the price of the other good, the price of good Y, does not impact the amount of X that you buy in any way. The two goods are unrelated. The cross-price elasticity of demand is always 0 if you're dealing with this Cobb-Douglas utility function. Interesting. So since that didn't take a whole lot of time, let's look at another example here of an analytic solution that we have looked at once before. Suppose we had perfect complements utility function, where your utility is the minimum of alpha times x, or 1 minus alpha times y. So you want to consume these things in fixed proportions. We did the derivation in another video. I can link to that, if I remember, in the description of this video. And we derived the Marshallian demand for x and y. Let's just focus on the one for x here. So the Marshallian demand for x is the budget divided by the price plus alpha over 1 minus alpha, those fixed proportions in which you want to consume x and y, times q. Let's go through the steps here again for the own price elasticity, income elasticity, and the cross price elasticity here. So we want to take the derivative of this function with respect to the price first. So price is down here in the denominator. In order to take that derivative, we're going to use the chain rule. And the chain rule, to think about it, make it a little more clear what we're thinking about here when we use the chain rule. This makes it more clear to me, and I'm sorry if I'm boring some of those of you who don't need it explained this way, but I certainly do when I think about doing it. Let's think about, instead of putting that in the denominator, let's write it this way: alpha over 1 minus alpha times q to the minus 1 power. The chain rule says if you have a function involving the variable you want to take the derivative with respect to, then the function here is just raising this inside part to the minus 1 power. And the chain rule, the way I think about it, is it says to take the derivative of the inside times the derivative of the outside. So the derivative of the inside with respect to p is simply 1. And then we multiply that times the derivative of the outside. Okay? Here's the way we're going to end up with here. The m, the derivative of the inside is just 1, times the derivative of the outside. Well, the derivative of the outside is minus 1 times, and then we take the derivative of that whole expression, basically, plus alpha over 1 minus alpha q, and to the minus 2. So we're multiplying by the minus 1 over here, and then subtracting 1 from that to get minus 2. But then we need to multiply by that p over x. But of course, we don't want to just leave that as x. We want the whole expression. So we're going to want that m times p plus alpha over 1 minus alpha q to the minus 1. So now we want to look for things that are going to cancel. So let's rewrite this. Here, let me move all of this up just a little bit here. So first thing we can do is we can cancel the m's. Here we have an m in the numerator. Here we have an m in the denominator. So we know that the budget is not going to play a factor in this own price elasticity here. And here we have this expression, p plus alpha over 1 minus alpha times q to the minus 1 power, but that's in the denominator of this fraction. So that's in the denominator of this fraction right here. So when we have something in the denominator to the minus 1, of course, that means we can put it in the numerator to the plus 1. So we could edit this a little bit by taking that p, and let's just write that p over there, times minus 1, and then pretend like this term here is in the numerator now, all to the first power. So since we have that same thing to the first power and to the minus 2 power, we can multiply those, add the exponents, and now that's going to cancel, and now that is going to simply be to the minus 1 power. So that's much simpler than what we had before, so now we can just kind of clean this up a little bit and rewrite it. We're going to have a p in the numerator, so we're going to have a minus p in the numerator. That takes care of the minus 1, and sorry, that p. And then we're going to have a p plus alpha over 1 minus alpha q in the denominator. And I don't see any obvious way to simplify that any further, so that looks like our expression for the price elasticity of demand for this good. And it's the sign is negative, and so it's as we would expect for an own price elasticity of demand. Okay, now let's rinse and repeat. Let's do the same thing, except now we're looking at how the quantity changes with respect to the budget instead of the price. So when we take the derivative, let's think about this version over here. If we take the derivative of that with respect to m, we can clearly see what we're going to have left is just this term here, p plus alpha over 1 minus alpha q to the minus 1 power. But then we have to multiply that times m over x. All right, so what we're going to do is rewrite, right? That's x. So rewrite that p plus alpha over 1 minus alpha q to the minus 1 power over there. Oh, I forgot something, and that's important, something. We forgot the other m, all right? So we forgot that m right there. And it's amazing how so many things, I guess it's not so amazing when you think about where all these things come from that we're dealing with, but it's amazing to me that all these things cancel. We have the m and the m cancel, and here we have the p plus alpha over 1 minus alpha q to the minus 1 power in the numerator. Same thing in the denominator. And look, every single thing cancels. And that means that we're left with the income elasticity of demand for this Marshallian demand function is always just positive 1. Interesting. Okay, one more. And I encourage you, if you've been watching so far and you haven't been active, please pause the video, take a minute, work on this one yourself. This one's a little harder. Things don't cancel quite as well as they did before, but give it a try. At least set this problem up. Get as far as you can. Pause the video. All right, so here's our demand function. We're going to take the derivative with respect to Q, which is the price of good Y. Since that Q is inside that function there, we have to use a similar kind of process that we did before. Use the chain rule. So we want to take the derivative of the inside here, that m, let's just write that m down first, multiplied times. The derivative of the inside is going to be alpha over 1 minus alpha. And then since that's q to the first power on the inside, that's the derivative of the inside. And then the derivative of the outside, we have that minus 1 multiplied times the derivative of the whole thing is the way I think about it. P plus alpha over 1 minus alpha q. Subtract 1 from that exponent and you get the minus 2 power. And then we are multiplying all of that times this price of good y over x. So q over, and then let's just go ahead and write our x here. Alpha over 1 minus alpha, q to the minus 1. All right, can you start to see anything that is going to cancel yet? Those m's are going to cancel. And then here we have this expression to the minus 1 power in the denominator, which as before means we can put that to the plus 1 in the numerator, which means that is going to cancel, and then this exponent is going to turn into a minus 1 when we add those exponents. So let's simplify and see what we have here so far. We're going to have a negative sign, or negative 1. Let's just put that out there so we don't lose it. Alpha over 1 minus alpha times p plus alpha over 1 minus alpha q to the minus 1 power times q. Now let's see if there's any way to clean this up in an obvious way here real quickly. Make it look a little simpler. I'm not seeing anything really obvious here. I think we can move some things around, but it's not really going to make it a whole lot simpler. We can just say alpha, here let me change colors here, that alpha and that q are both in the numerator. Everything else is going to go in the denominator. We're going to have that minus sign. We can put that up top. 1 minus alpha times P plus alpha Q over 1 minus alpha. But that looks like about as simple as this is going to get. There are a few ways we could rearrange things. So nothing really super interesting there about that cross price elasticity of demand, unless I am missing some obvious way to simplify that. But we did get some very interesting, simple results when it came to the income elasticity for this kind of situation. Always 1. The price elasticity of demand was not too complicated. Own price elasticity of demand, not too complicated in this case. Shockingly simple result for the Cobb-Douglas utility here. Always -1 for the own price elasticity. Always +1 for the income elasticity, and always 0 for the cross price elasticity. So I think that's enough senseless math for one video. If you have any additional questions, or if there's something I went through too quickly, skipped over, anything you want clarified, please let me know in those comments down below. I always appreciate your comments and your suggestions. It helps me do this better. I enjoy going through these problems because I need it to keep myself sharp. So I'm not used to explaining these things to other people. If I've been sloppy or careless or haven't explained anything well enough, I really appreciate your feedback. That's all for me. I'm signing out, and good luck with your economic studies, everybody.